In this video we're going to look at the idea of differentiability, which is basically can you find a derivative, and whether a function is differentiable or not. And if it is described as being differentiable, what does that actually mean? So a differentiable function is a function whose derivative exists at each point in its domain. So we've got some different definitions of a derivative. We know that the derivative at a point, or the derivative of a function at a point, is equal to the gradient of the tangent at that point. So for this function over here, for any point a, the value of the derivative is the gradient of that particular tangent. So as long as that tangent has a gradient that is defined, that has a value for the gradient, then we have a derivative. And the only time that the gradient of a straight line is not defined is when it's a vertical line. And so we have that the derivative will exist if the tangent at that point is not vertical. If you've got a vertical tangent, you won't have a derivative. The other definition of a derivative that we have is that the derivative is the limit of the gradient of that line. So this is the gradient, this is the slope formula for that function for f of a. So what we're actually looking at as let me just zoom in a little bit here. So what we're actually looking at is as this x value gets closer to a, as this point becomes closer to a, we're looking for the derivative to be what is the gradient of that line, and then when x is here, what is the gradient of the line that joins it to a? What is the gradient of the line that joins it to a? That's the definition of the derivative. It is the limit of the slope of that line. And for a derivative to exist, you need the left-hand limit to be equal to the right-hand limit. And so that becomes an issue when you have graphs where the slope of the line changes quickly, changes at a particular point. And the points that where the gradient changes quickly, this green point here, let me just move this over here, this green point here, are what we refer to as cusps. Now, for the limit to exist, the limit must be the same on both sides of that point, which has implications for endpoints. We'll talk about those in a minute. So if the limit must be the same on both sides, then the slope must be the same on both sides of that point. And if the slope of the function is the same on both sides of that point, then the function will be what we refer to as being smooth, so that there will be a nice smooth change from sloping up maybe to sloping down, or sloping down to sloping up, nice and smooth at that point, not a sharp point. Although in some situations, we'll look at in a minute, one that looks pretty much exactly like this, the derivative does exist because the slope approaches the same value on either side. Let's investigate that a little bit more. So let's have a look at an example of a hybrid function that is continuous. It contains a cusp here, and let's see if we can determine whether this function is differentiable at this point or not. And so the question asks us to first of all sketch the graph of the derivative function, and then state the domain for which the derivative function is defined. So the first thing we're going to do is we are going to find the derivative. And so we find the derivative by finding the derivative for each branch of the function. So the derivative of the yellow function is 2x plus 3, and it has the same domain as the original function. And the derivative of the second branch, so the derivative of 3x plus 2 is 3. for x greater than or equal to 0. So if I sketch both of these branches, so that the straight line for x is less than 0, you can see it's got an open circle there, and then 3, you can see that the derivative function is in fact a continuous function along here. And so the domain for which the derivative function exists is in fact all of R, and the function, the derivative function itself, is continuous. And so what we're looking at in the original function is that as we move from the left hand side, the slope of the line is approaching 3, and as we approach from the right hand side, coming back this way, the slope of the line is approaching 3, and in fact the slope of the line all the way along here is 3, because the formula for the line is 3x plus 2, and the slope of the line is the gradient, and it's a 3. So let's look at the relationship between differentiability of a function and the continuity of a function. If a function is differentiable at a particular point, then the function is continuous at that point as well. So if it's differentiable at a point, it has a smooth curve at that particular point. And so differentiability, or being differentiable, implies the continuity of the function. It implies that f of a exists, and it implies that the limit of that particular function exists. However, the converse is not true. Continuity does not imply that a function is differentiable. For example, the function x to the power of a third is continuous. Here it is here. There's its graph. But it's not differentiable at x is equal to 0, because at this point here we have a vertical tangent. So if you remember, x to the power of a third is the inverse of x cubed, and the derivative of x cubed is equal to 0 for x is equal to 0. So at the point x is equal to 0 for our cubic function, I'll just draw it over here, here's x cubed. At this point here we have a horizontal tangent, and dy dx is equal to 0 at that point. And when we turn it into an inverse, of course, the horizontal tangent becomes a vertical tangent. Okay, so the reason for that is that continuity is looking at whether the actual function exists, and differentiability, although it is also a limit, it's actually the limit of the slope of the line. So it's not the difference between the two. One is the limit of the function, and the other one is the limit of the slope of the function. So if we have a function that is not continuous at x is equal to a, so there's some kind of discontinuity there, there'll be a jump, a gap, a hole, then the function won't be differentiable because the slope of the line won't be smooth. So let's have a look at some discontinuities. So these are particular functions that we've got here. These are f of x. And remember, if we're looking to see if a function is differentiable at a point, so let's look at this point here, x is equal to a, what we're looking at is the slope of the function. So the slope of that white line. So there's our a value here, and if we're looking from this side, if we pick an x value, we're looking at the slope of that line. How sloped is that line? As we move closer, if we pick another x value in a little bit closer, the slope is still 0. So our limit as x approaches a from the negative direction for slope is equal to 0. If we do the same thing from the right hand side, so looking out on the right hand side, we're going from this point up to our f of a value. We're looking at the slope of that line, which is fairly steep. And as we move in, it becomes steeper and steeper. And so what we're actually getting is eventually we'll get a vertical line. And for that, we know that the slope is undefined. And so the limit for the right-hand side is undefined. And so we don't have a derivative for this particular function at that discontinuity. So if we look at the second graph and do the same thing, from the left-hand side as we come in, we're looking at the slope from that point on the line to this point for the function. And so we're looking at a steep slope here. And as our x value moves in closer and closer, you can see from the left-hand side, our limit for the slope is approaching infinity. It's becoming vertical. And so again, our slope is undefined. So our function at that point is undefined. So let's look at an example. The graph of the function f is shown below. It has a horizontal tangent at x is equal to minus 3. So at x is equal to minus 3, which is here, it has a horizontal tangent. And it also has a horizontal tangent at x is equal to 2. So there's x is equal to 2. It has a horizontal tangent. And it has a vertical tangent at x is equal to minus 1. So it's got a vertical tangent here. List all values for x where the function is not differentiable. So functions are not differentiable at jumps, and they're not differentiable at vertical tangents. So we have both of those in our image. We have a jump here at x is equal to minus 5, and we have a vertical tangent here at x is equal to minus 1. So both of those values, x equals minus 5 and x equals minus 1, are points where the function's not differentiable. The other point I want to have a look at is the end point over here. And let's talk about whether things are differentiable at an end point. So for a function to be differentiable at a particular point, you need the limit, you need the derivative to exist. And for the derivative to exist, you need the limit of the slope to exist. And for the limit of the slope to exist, you need the left-hand slope to be equal to the right-hand slope. And what we've got here is a problem. We have a right-hand side of the slope doesn't exist. And so what we have is that the end point is not differentiable. And so we also have a point at x is equal to 5 that is one of our not differentiable points.